Right, our guideline for unusual or unlikely is 5% or less. Is this 5% or less? Yes, so it's unlikely. Good? Less than 1%, yeah. You're right, so it's definitely less than 5%.
So Professor, so when we have answers that are like 0.000 whatever, and it says to the third decimal, so you want us to do the last three whole numbers?
So this is 3 significant digits, which
Okay.
is not the same.
Right.
This is 5 decimal places,
Mhm.
but 3 significant digits.
Yeah.
These 3 are significant.
Okay, cool.
Yeah. 3 sig figs is usually pretty good. Because otherwise, if it's less than that, then you just would put like 0, 0, 0, right? If you did like if you did this to 2 decimal places, it would just be 0. And we want a little bit more than that. Yeah. Thank you. Good question. Now, this is just pointing out that again, the one you did earlier, they're independent because we replaced the marble afterwards. So you just multiply the probabilities. But the next one we're going to do is going to be when they are dependent. So instead, you find the probability of A, so you take that path, and then you find the probability of B given A has happened. From A, where the probability of B given A has happened. So we're going to take a look at this right now with the dependent. Here is an example. Remember we said that yellow and male were dependent? And remember we multiplied the probabilities, it didn't work out? So here, first off, what's the probability that you are a yellow male puppy?
4 out of 20.
Yep, male and yellow is there's 4 of them out of 20, 4 out of 20. Great. And these guys are not independent, so we're going to use the probability of A and B is equal to the probability of A times the probability of B given A has happened. All right, so what's the probability of A? Let's make it into things that we're familiar with. So this is male and yellow, right? So we'll call it the probability of male and yellow is the probability of, I'm going to do yellow. Yellow given the probability of male given yellow. Is that okay? So what's the probability of yellow? What's the probability you pick a yellow puppy?
6.
Yeah, there's 6 of them out of 20.
Yes.
What's the probability that they are male given it's a yellow puppy? So in other words, you know it's a yellow puppy. It's one of these 6. What's the probability you pick a male puppy? 4 out of 6. Everybody see that? Circle them. If you get a given, just circle that group. It'll make your life so much easier. 4 out of 6. And look how nicely that 6 over 6 is just another form of 1. They go away. And I'm left with, oh, sorry. Sorry, I misread it. This is 6 out of 20. My bad. Did I totally screw people up with that? Sorry. Probability that he's yellow is 6 out of 20. Okay. So sorry. So the probability that they're male and yellow is 4 out of 20. And, not surprisingly, that matches up with what we know should be the case. Everybody good? Until I totally screwed that part up? All right. So you guys go ahead and do problem number 6. We'll take a break in just a minute, but I need you guys to do problem number 6 first. So,
Oh, it's that thing. That's right. I got it.
so I need you to draw a tree. It says, make the first layer of branches risk. How many risk options are there? 3. What are they?
Low risk, medium risk, and high risk.
Low, medium, high. So you should have 3 branches. One that goes to L, one goes to M, one goes to H. And then write in the the probabilities of each branch. Here's the thing. Change your percentages to decimal. It'll make your life better. Usually you do fractions, but if we give you decimals or percentages, do them as decimals. If we don't, then do them as fractions. That's the kind of general rule. If you're given decimals, then do decimals. And percentages are really decimals. So we should have 3 branches, medium, high, and percentages on each branch. Let's do them as decimals. And then, what's the other thing we know about these drivers? What's the other thing we know? If they're in an accident. So, don't say it out loud, but either you were in an accident or blank. Those are going to be your options. The other thing is, if there's a 1% chance that you're in an accident, then there'd be a blank percent, right? It just sort of, if there's a 10% chance of rain, then there's a what percent chance of no rain? 90%. 90%. Make sense? That's add up to 100%. Right? So either you're in an accident or, what's the other? Either you're in an accident or you're not in an accident. If there is a 1% chance you're in an accident, what's probably you're not in an accident? 99%. And remember, we want to find all those little bits. We want to find all the accident people. So you gotta figure out how do you calculate these guys here? Okay, so the first one is 0.60 times 0.01, 0.006. Next one is medium risk and accident, so 0.30 times 0.05, so 0.015. And this one here is 0.10. Again, right, remember, to find the end, you just multiply along the tree. So if I want to know here, I just multiply the pathway, along the pathway to get this. So then we have these 2.009. Here's the deal. Can I be a low-risk driver and a medium-risk driver? No, it'd have to be a low-risk driver or a medium-risk driver. Everybody follow? So either I was low-risk and had an accident, or I was medium-risk and had an accident, right? Or I was high-risk and had an accident. So ors, this is this or that, ors we add, thank you. So then we end up getting 0.03. Good? 3% chance. Perfect. Now, the challenge, did anybody else get the challenge? Sterling and Gang got it? Right? Anybody else get the challenge? Yeah. Good deal. So, who would like to explain it? Do you want to explain it, or do you guys want to explain it? Who wants to explain it? So the challenge is, if someone has a high-risk accident, find the probability they're high risk. So, here are all my accidents, right? What's the probability? So, okay, if someone was in an accident, what's the likelihood they came from the middle risk group? How many of this 3% came from the middle risk group? Half of them. Does that make sense? Half of them came from here. Does everyone see that? In other words, 0.015 over 0.03. Here, I'll add another zero here. So they have the same decimals. So kind of think about kind of like 15 out of 30 sort of in a way. Does that, you know what I'm saying, sort of? About half of them. So you can kind of, if you kind of think about it this way, like kind of 9 out of 30 came from here. So think about like, here's 1,000 people. 1,000 people, 10% of that, 100 of them are high risk. Of those 100, 9 of them had an accident. So it's kind of like 9 out of 1,000, 9 thousandths. 30 people had an accident, 9 of them were high risk, 15 of them were mid risk, and 6 of them were low risk. You can kind of think of it like that. So 9 out of 30 were high risk. So the probability that if they had an accident, the probability they were high risk was 9 out of 30. Does that sort of make, you guys kind of follow me?
Yeah.
Okay, good deal. So that would be 0.009 over 0.030, which ends up being 30%? 30%. Good? All right, cool. That leads us really nicely into this Bayes' theorem and other stuff. Right, so conditional probability, first of all. Conditional probability, if you want to know, sometimes you want to know the conditional probability. Like in the last one, I want to know what's probability that you're high risk given you had an accident. And so what you do is you find the probability that they're high risk and had an accident divided by the probability by the probability of having an accident. How do we get this formula? It's not a new formula. It just comes smack out of here. Do you guys recognize this one? This formula? Everyone recognizes this one? That's just a regular multiplication formula. What you do is, you take that, and you divide both sides by probability of A. What happens when I do that? These go away, and I'm left with probability of B given A on this side equals probability of A and B divided by probability of A. Boom, done. So this is just a rearrangement of this formula. It's the same formula. Just dividing both sides by probability of A. Okay. Now Bayes' theorem, that's kind of what we just did last problem, that last challenge problem, is super similar to this. It's basically the same thing, only they spell out how do you find the probability of A and B. Well, you find the probability of A given B and multiply that by the probability of B. So we just kind of use this thing down here. We'll look at it. Right, so we wanted to know the probability of being high risk given you had an accident. So what we do is we found the probability of having an accident given you're high risk, multiplied by probably you're high risk. So remember the high risk was 10%, right? 10% of people had high risk. If you're high risk, then the probability of having an accident was 9%. And then we divide it by the probability of accident. So that's where that comes from. Bayes goes on and becomes more complex, but this is the basic, simple version of Bayes. We are required to teach it. It's in the syllabus. The UCs kind of want it there, and the Cal State East Bay, the East Bays want it there, or not the East Bays, the Cal States want it there. So you are not going to have any homeworks on it or test on it. I decided actually I'm going to take out conditional probability pretty much entirely. That's what I kind of covered. I've thought about it and decided it's not that important. So we are going to skip the problem at the bottom. So just write skip on the bottom through that one. We're going to skip that one. That whole bottom, little bottom section, there's like a little bit that below this formula. So it's really just, it's just this tiny bit right here, right? Find the probability that the respondent was male. Just skip that one. Because looking at our time frame and everything else, I've covered it. We're done. Okay, turn to the next page. So then lab problem 1, which is basically the same sort of concept. We're going to skip that one also.
See which one?
Wow.
Lab problem 1,
That problem.
skip that one, just the one. And I am 98% certain I've taken it out of your homework. If I haven't, please let me know and I will delete it out of your homework. Which leads us then to the next step. Oh, and you know, this also is not important, but it's kind of fun, so I'm just going to talk about it for 2 seconds. So the probability of getting a 5-card flush in poker, that's all the same suit, would be, well, say I wanted to get hearts. There are 13 out of 52 hearts. So the probability of getting the first card being a heart would be 13 out of 52. Then after I take that heart out, I now have 51 cards and only 12 of them are hearts. After I take another card out, then I only have 50 cards, 11 are hearts. Take another card out, 49 cards, 10 are hearts. I take out another card, and then the last card would be, there's only 48 cards left, and 9 of them are hearts. Yeah, I need the first heart and a heart and a heart and a heart and a heart, so you multiply those probabilities. And then there are 4 suits, so you need to multiply by 4, because you can also do that with diamonds, clubs, and spades. The other way you can do it is that it doesn't matter what the first card is, just whatever suit that is, the rest of them have to match it. So you can just do it this way also. They both end up being the same answer either way, because this is the same, and 4 times 13 is 52 over 52, that's just 1. All right, again, not important, but interesting, for me at least. Okay, so now do lab problem number 2. This is almost exactly like your problem from last class, only now we're not replacing it. We are drawing a marble, and we are not replacing it. So I have 10 marbles, right? 10 marbles, and pretend like the white are really blue. And I draw one. What can I possibly draw? What are my possibilities? What are my possible outcomes? A blue one, or a red one, or a green one. So you should have 3 branches, right? Don't do 1 for every single marble. Don't do 10, because then you have to do a whole bunch off of each of those, and you're going to have this nightmare. You're going to need a giant page, and you wouldn't have time for that. You don't have space for that. So just combine them, like all the reds, combine them into 1. All the blues, combine them into 1. And so they're not going to be equally likely. They're going to be different probabilities on each branch, just like the last problem you guys did. And then I draw a marble. Say I draw a red one. Now, how many marbles do I have left in the bag? I only have 9 left, right? Because I draw one, I'm not replacing it. So think about that as well as you're doing all these. Another comment, this means the probability that I draw a red on the second draw given I drew a blue on the first draw. So that's what this means. A red on the second given blue on the first.
Are these independent
These are dependent draws because I'm not replacing, remember? So if I'm replacing, it's independent. If I don't replace, they're dependent. Depends on what you drew first.
Does each letter represent a new, or does each letter represent the same? It's a consecutive draw. Red, then green, then red.
Red, green, blue, and then you have a second layer of branches for the second draw.
So all the letters over there are in relation to the original drawing. Is that what you're saying? Are these different drawings? Each drawing. Does that make sense? Am I asking you?
You're drawing 2 marbles. Make a tree. So everybody draw a tree. Everybody make a tree. And then answer those questions. Probably draw a red marble, then a green marble. Because you're drawing 2 marbles. If I drew a red marble, what can I draw next? How many marbles do I have left? 9. How many of them are, what can I possibly draw?
Red, white, green.
Red, white, or green. So in this case, red, blue, or green. What's the problem? How many are red?
2.
Out of how many?
9.
So let's probably draw a red one.
2 out of 9.
2 out of 9. How many are green?
1.
Out of?
9.
What's probably draw green?
1 out of 9.
1 out of 9. How many are white? 6 out of?
9.
Now, so that's for the first one. That's for this one. What if I drew a green one instead? Oh, different scenario. Now I've drawn a green one, different step. Now what can I draw next? Red or white? Is that everyone following?
Yeah.
Okay, so if I draw a red one first, what do I have left? I have, so here I have red, okay, here I'll do it like this, sorry, my bad. Here I have red, 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 green, blue, 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 blue. Everybody on board? I draw a red one.
This is why it gets confusing.
What do I have left?
You have
Red, red, green, and what? Blue, 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 blue. Everybody on board? If I draw a red one out of here, then this is what I have left. What can I draw for? What can I draw next? Red, or what's probably I draw a red one? 2 and 9. Green one? Blue one? Okay, but what if instead I drew a green one? Now what do I have left? This is what I had. I didn't go this way. I did not draw a red one. Instead I drew a green one. What do I have left? 3 reds and 0 green and let me make it clear. These are different pathways. You could take the red pathway or the green pathway or the blue. You're not taking all of them. You're just taking one of them. If you went this way, that's what happens. If you went this way, now you got this instead. Do you see what I'm saying? They're not the same. Figure out what would happen if I went this way. And figure out what the probabilities are here and here. And then answer those questions.